Hello, good morning everyone. Let's get started. Today we'll look at the knapsack problem. Primarily, you can look at the knapsack problem as you have a big box to fill up and you have limited capacity of the box, how much to fill up. For example, let's say you're traveling by air, and when you're traveling by air, you have a suitcase to carry, and suitcase airline says you are allowed only 15 kg of weight in the suitcase. Now your number of clothes to carry and weight of total clothes, your stuff, personal stuff, baggage, your other stuff, it becomes 25 kg. But you're allowed to carry only 15 kg. How do you decide which clothes or which packing to put in suitcase and which idea to leave behind? And precisely that is what in knapsack problem is we are looking at. So let's look at how do we go about doing it, how do we solve it, address it. Primarily, this lecture is part of my material and partly, if you look at textbook, it is textbook number 2, which is Horowitz Sunny, section 4.3 under greedy algorithms. And then I look at reference book Corman. They also talk about under what is called greedy approach to knapsack problem. So let us look at the what really is knapsack problem. I'll give a simple example which you can correlate, and then you go into, hello, am I audible? Can somebody confirm, am I audible?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yeah, because Chandan is saying not audible, so that's fine. Chandan, you have to look at your mic, your speaker, it may not be working. So let's look at that you are a flower vendor or we see street flower vendor. He or she needs to sell flowers, and the vendor buys flowers from our KR market and sell during the day. And KR market put a restriction that for any vendor, they'll basically put this kind of limits that no vendor can buy more than 8 kgs of lilies. And if a vendor buy 8 kgs of lilies, so the limit when you're looking at the 8 kg limit means a vendor can only for lily vendor she or she can buy only 8 kg, not more. But if she buy 8 kgs of lily, sells it in the day, total profit she makes is 240 rupees. Similarly, roses limit is 10 kg. You cannot buy more than 10 kg of roses. If you buy 10 kg in assuming you sell everything, you make a profit of 250 rupees. We assume that at the end of the day, the vendor is able to sell everything what he has bought from the KR market. Another flower, which is basically jasmine, one can buy only 6 kg and it gives you total profit of 120. And then daisies with again 6 kg and total profit is 210. Now vendor has a bag of 20 kg. So look at there are only 4 varieties available. Total weight is 8 plus 10, 18 plus 6, 24 plus 6, 30 kg. So total weight available is 30 kg. But vendor has a bag of 20 kg. Now question is, what does vendor do? Which varieties should it buy from KR market to sell so that its profit is maximized? And then basically we look at how does greedy approach would solve this problem. Jana, you see you can't hear me, but others are able to hear. So look at your speaker. Jana, are you able to hear me? I'm assuming others are able to hear, so my voice is audible. For those who can't hear, so please look at your speaker. That may be in silent mode or something. So get out of that mode. That should be fine. So let me continue. At any point in time you see a voice problem, let me know so that I can take action accordingly. Now, so let's look at what you're saying is if a street vendor, a flower vendor has to buy and roses of 10 kg gives a total profit of 250 rupees, lilies 8 kg maximum you can buy 240 rupees profit, daisies 6 kgs and jasmine 6 kg. So question is, and vendor has a bag of 20 kg, how should vendor go and proceed? So this is a one sample instance of what is called a knapsack problem. I'll give you different approaches and I'll tell you how do we look at the problem and then what would be the more optimal, more greedy approaches. Probably no, but let's look at what is that we really want to do. So fundamental question is which quantity of each flower vendor should buy. So one approach is, look, what I take is I have 4 flowers. I want to be fair. I buy equal quantity of each flower. That means as a vendor, I buy 5 kg of roses, 5 kg of daisies, 5 kg of lilies, 5 kg of jasmine. Total become 20 kg. So I buy 5 kg of each. My total profit earned is, roses would give me, remember 250 is the profit on the entire 10 kg. So per kg profit is 25 rupees. So for 5 kg my profit becomes 125 on roses. Similarly for lilies, my profit becomes 240 by 8 into 5, 150 rupees profit on lilies. Daisies per kg I get 35 rupees. I make 175 and jasmine, and my total profit happens to be 550 rupees. So if I were to take an approach that I buy each flower in equal amount, then my profit is 550 rupees. Objective of vendor is to maximize the profit. Let's look at another approach. And another approach is that I buy the flowers in the ratio they are available. Total is 30 kg available. I can carry only 20 kg. So roses I'll buy 10 by 30 into 20. Okay, that's the capacity. So in equal proportion. So that means I buy roses 10 by 30 into 20, which is 20 by 3 kg or 6.6 kg. Lilies, I buy 16 by 3 kg. Daisies, again 6 by 30 into 20, and that means, so I'm buying 4 kg of daisies, 4 kg of jasmine, 5.3 kg of lilies, and 6.7 kg of roses. Given that if you buy, let me calculate what is my profit would be. Remember, roses, my profit per kg is 25 rupees. For lilies, my profit per kg is 30 rupees. Daisies, my profit is 35 rupees. And for jasmine, my profit is 20 rupees per kg. So profit earned for the day, roses gives me 166 rupees. Lilies gave me 160 rupees. Daisies give me 140 rupees. And jasmine gives me 80 rupees. And total profit is 546. In previous case where I was buying equal amount of each flower, my profit was 550 rupees. If I'm buying flowers in equal ratio, my profit is 546. Let's look at other approaches possible. The human mindset is typically, that always happens, that you buy things which have maximum profit. So we know that maximum profit is buy from roses, which is 250 rupees. So first let me buy all the roses. Then I buy whatever possible lilies. Then I look at jasmine. So I sort the flowers in terms of total profit available and buy accordingly. So that means I'll buy roses at 10 kg. I would buy, once I buy roses 10 kg, my bag is 20 kg. So I'm left with 10 kg of weight. Then I buy lilies 8 kg. So I 8 kg of lilies, this 10 kg of roses. I'm left with 2 kg weight now. So I buy 2 kg of daisies and I'm done, got 20 kg, and I don't buy any jasmine at all. given this scenario that I buy this much, what will my profit be? Can somebody calculate and tell me what the profit be? Can quickly somebody tell me how about the so that you can understand what I'm trying to do? Can somebody put me in chat box or speak what the total profit when I buy this kind of amount? In first approach, my profit was 550 rupees. In my second approach, it was 546 something. What the profit in this case would be? Can you quickly calculate and give me the answer? Anyone? Nitish, Noor? Yeah, so profit is 560 rupees. So if you look at Rogers gives me 250 rupees profit. Then I get 240 rupees profit from Lily's. This makes it 490. I have Daisy's left 2 kg. This will give me 70 rupees profit. So 490 plus 70, my profit is 560 rupees. So my profit has increased. Can I look at another approach? Approach number 4. Rather than looking at the ordering my profit, I said let me fill up the smallest quantity first and then keep building it up. That means first I buy all the jasmines, 6 kg, then I buy all the daisies, then I buy all the lilies, whatever possible, and then look at it that way. Buy as per capacity means keep filling whatever the lowest quantity available first. That means I can keep getting maximum of number of varieties. So I fill up lowest quantity and then fill up. So when I look from this, my jasmine 6 kg, daisy 6 kg, lily 8 kgs, and this makes 6 plus 6 12 plus 8 20. So I don't buy any more roses. My profit, jasmine gives me profit of 120. Daisies gave me profit of 210. I'm left with now, I've already bought 12 kg stuff. I'm left with 8 kgs. I buy 8 kgs of lilies. This gives me 240 rupees plus 8 kg. I got 20 kg. So my total profit now is, if we look at 570 rupees. So my profit has become first approach 550, second approach 546, third approach 560, fourth approach 570. Is there a better approach? My objective is to maximize my profit. So ideally, the most ideal approach would be that I look at which flower gives me maximum profit per kg of flower. So rather than looking at total maximum profit in the order or looking at total minimum weight, I should look at which flower gives me maximum profit on per kg basis. That being the case, let's calculate and use that approach and see what is that it basically gives me. So considering that, I look at my approach is get maximum profit on per kg of flowers. So I know that roses gives me 25 rupees of profit per kg. My lilies gives me 30 rupees of profit per kg. My daisies give me 35 rupees of profit per kg, and jasmine gives me 20 rupees of profit per kg. So that means I should first pick the daisies where they give me maximum profit. Then I pick lilies that give me 30 rupees profit per kg. Then I pick roses, and if I still have a space, then I pick jasmine. If I take that approach, the way I would take is these are my profits: roses 25 rupees kg, lilies 30 rupees kgs, daisies 35 rupees per kg, jasmine 20 rupees per kg. So I'll buy first all the daisies, 6 kg of daisies, then I buy 8 kgs of lilies, I'm left, I've taken 14 kg, 6 plus 8, 14. I'm left with 6 kg. So I buy 6 kg of roses. And when I do that, my profit actually becomes roses gives me 150 rupees, lilies gives me 240 rupees, daisies gives me 210 rupees. Just means there is no profit. My total profit is 600 rupees. And you figure out this happens to be the best approach in the current case, and this also gives me what is called the optimal approach. I cannot do better than that. So basically I am being greedy, and my greed is I should buy that flower which gives you maximum profit per kg, and that is what we call is greedy approach, and that's basically what we do in our knapsack problem. So you can look at my vendor bag as a knapsack. Quantity, I'm looking at flower, any item, and there's a profit per them, and there's a weight, and that essentially we look at the knapsack problem. So we look at 5 approaches. First approach, remaining 3 are greedy. I'm looking at max highest profit or smallest capacity or max profit per kg, and we show that the approach 5, the greedy approach, still gives me the maximum profit, and this also what call is gives me the optimum. Since we can buy any quantity of flowers, it could be half kg, 1 by 3 kg, quarter kg, whatever, and this is called fractional knapsack. Meaning I don't have to buy whole jasmine or whole of roses, but I can buy part of it. If I have to buy whole thing as a one go and not part of it, that is called 0-1 knapsack. And if I'm doing 0-1 knapsack, we'll see that this greedy approach does not give me optimal solution. This gives me optimal solution if it is fractional knapsack, but does not give me optimal solution for 0-1 knapsack. That means I need to buy the whole 10 kg of roses or 8 kgs of lilies, something of that kind. Any questions so far? And otherwise, can there be multiple optimal solutions? Yes, there certainly can be multiple optimal solutions. Like if both roses and lily have same profit 25 kg, then I can buy 1 kg of rose, 5 kg of lilies, or 2 kg of rose, 3 kg. I can do any variation. So all different solutions can still give me same optimal because I am trying to maximize the profit. If any questions, let me know. Otherwise, I'll proceed. As I said, you can look at same way, like you're traveling by air, and airline has put a limit of 15 kg on check-in bag. There are number of things to carry. Now, how do you decide which item to carry? That depends on priority. If you are a student and some books are important, you'll first carry the books. If you are going on a trip, you like to keep goggles, other stuff. If you are going on a wedding or some function, you probably want to keep your suit at the highest priority. Based on that, we got to decide the profit and look at it. So formally, we can define the knapsack problem as given an objects, like we have seen in flower case, given 4 objects and a knapsack bag with a capacity like vendor bag at 20 kg, which is M is 20 kg. We need to fill the knapsack so that we maximize the value as a profit, such a way that we know each object has the weight I, which is given there. The roses, lilies, same way. Each object has a profit associated with it, and we want to maximize the profit. And that means we can say, if you choose a fraction, we can choose part of it. But if you take a value 0, means you're not picking that item. If you took a value once, that means taking the entire item, or we can take a parcel of it, and such that we would like to maximize our profit. So our problem basically becomes that maximize my profit pi xi. Xi is the amount, fraction of the amount for the object I we are buying with the weight wi. Ith object weight wi. So we want to maximize our profit pi xi subject to that my weight wi xi is less than equal to m. If I can make it equal to m, great, but this cannot exceed m because that's my maximum size allowed. So objective is maximize this profit pi xi subject to the weight sum over wi xi for all the items is equal to less than equal to m, And that's precisely what we call is knapsack problem. And that's what we'll do and formally solve the problems with this approach. So let's look at how do you do that. And so xi minimum value could be 0, max value is 1 means we're taking the entire weight wi, 0 means we are not looking at that item, then any value 0.1, 0.2, 0.25 is taking fraction of the weight. And for all the items we do that. So let's look at precisely, I'm not taking an example from a book. In the example from book, this Bahru Visani, the 3 objects given and my capacity is 20. Profit per object is 25, 24 and 15 and weight per object is 18, 15 and 10. So we need to pick the object such a way that my profit, this profit is maximized subject to that my bag weight is 20. That means I cannot pick all the elements, but if I pick all 3 elements, my total weight becomes about 43 kg, which I cannot. So what should I do to pick up these objects? And there are different solutions there. So one solution is, I'm giving you the different solutions, we'll discuss them in detail. So one approach is take some random weights. So I take first item, first item, we take half a unit, that means we take 9 kg. Second item take 1/3, that we take 5 kg. Fourth item we take 1/4, which is 2.5 kg. So total weight is 9.9 plus 5 plus 2.5, which is 16 kg, 16.5 kg. And if I look at the profit, that means profit is 1/2 of 25 plus 1/3 of 24 plus 1/4 of 15. My profit becomes 24/25. Other approach could be, I look at the highest profit first. That means first I pick P1 item completely, and then I pick P2, and then 3, and so on. So if I pick P1 completely, I get already 18 kg. I'm left with only 2 kg to fill up. But to take second item as 2/15, my profit would be accordingly 25 plus 24 into 2/15, and my profit is 28. Other approach is, I start from filling from lowest weight side so that I get maximum weight. So I basically say lower weight first. So my W3 is 1. I take it in full, and W3 1 means I already got 10 kg weight. I'm left with 10 kg. So I take 10 kg of second weight, which is lowest 15. That means I take 2/3 of this weight, and I don't take anything first, and my profit accordingly becomes, look at in this case, my weight is 20 kg, my profit becomes 31. Or I take my same greedy approach, look at the item which gives you maximum profit per unit of weight. So look at maximum profit per unit of weight. That means order them in the ratio of Pi/Wi, pick up the item accordingly. And when I do that, look at profit for first item is 25/18, for second 24/15, for third is 15/10. This happened to be the highest. So we take all the items of this, then this is highest and this is the lowest in the order. So we pick up, my profit becomes, and this is what we call is greedy approach to knapsack problem. So if we look at, well, basically what we're doing is, remember when you look at last class, the greedy approach problem says a subset problem, given a set of elements, pick up some subsets of it so that my profit is maximized or my cost is minimized. So greedy approach basically fits into my subset paradigm, because given this set of n objects, I'm not taking all of them, I'm taking only some of them. And then it should be fine. Again, I'm getting a message from this one that no voice. Are you able to hear me?
Yes, sir.
Okay, thank you. So Yaswant, you need to look at, if others can hear me, then mic is not a problem, you have to look at your side. and verify something is wrong in the audio. So let me continue. So basically, we look at different strategy. One is object with highest profit, or taken fractions, and possibly we'll see that some object we can put in last. Everything cannot be taken in full. The last object has to be partially. So the approach one, we took in the profit of this. Other is fill my knapsack with maximum number of items. That means start filling with lowest weight, keep filling it up. So fill knapsack as slowly as possible, meaning keep filling from lowest weight items, and that is second approach. And then I'll look at what we see in the previous case. And third is non-increasing. So sort them out in decreasing order, Pi by Wi. That's what non-increasing means. The two could be equal. There's a basic difference between non-increasing and decreasing. Decreasing meaning every item, next item would be less than the previous item. Non-increasing means every subsequent item can be less or equal to but cannot be more. That's the meaning of non-increasing. So understand the difference between non-increasing versus decreasing. We'll use the word non-increasing because weights could be the same. So we sort that out in our case. So look at P2 by W2, P3 by W3, P1 by W1. P2 by W2 is, so P1 by W is 25 by 18. This P1 by W1, P2 by W2 is 24 by 15, and P3 by W3 is 15 by 10. So this gives you your maximum value, and this is the next highest, this next highest. So my sorting order is, first is P2 by W2, second is P3 by W3, third is P1 by W1, and I pick in that order. That means P2 I'll take it in full, X2 is 1. When I take X2 is 1, I already taken 15 kg of weight. I left with only 5 kg in my capacity. That means I take 5 kg. Next item is P3 because this is in that order. So I take 5 kg of this. That means I take only half the item, and so at my X3 is half. Now my bag has become full 20 kg, and that means I cannot take the first item, and so my X1 basically becomes 0. So if I calculate my profit for the second item in full is 24 rupees. So I get 24 rupees of profit. For second item, I'm taking half the weight. For the X3 is half the weight. So profit is half of it, which is 7.5. And third, I'm not taking any weight at all. So my profit from first item would be 0. So my total profit is 24 plus 7.5, which gives me 31.15, and that's the maximum profit we basically get. And that's precisely what a knapsack problem is. And we say the 0-1 knapsack problem gives me optimal solution. So fundamentally, and we look at this approach. Depending on the problem, we define our criteria. What is the good approach to take? That gives a maximum profit. And we look at different problems. We look at job scheduling. We look at our Driscoll algorithm. We look at prim tree, sorter's path, Dexter algorithm, all-pairs sorter's path. All of them follow greedy approach, and we look at what is the approach I need to follow, what is that I need to maximize, and then we follow from there and continue. So essentially, keep picking the object in the order of highest profit per unit kg of weight till, and we can't take object in full. We can't take in full, take a fraction of this and fill and I should be done. And we look at why this is optimal. When you do a proof, we look at the mechanism. That mechanism is assuming our solution approach is not optimal. That means that the solution which is optimal, we'll compare our solution, see can we compare that, make it equivalent and see are we optimal or not, and we prove that we are really optimal, and that's the approach we'll basically take. So formally I can define my NEMA problem is, now how do we say optimal? First case is if sum of all quantities less than m. An object, my capacity is m, but total weight is less than m. That means I picked all quantities. I cannot pick anything more. So that's the optimal solution. Nothing to worry about it because I picked all the items. I cannot pick anything more. So this is what we call is trivial case. So let's consider a case where sum of all quantities is greater than n, exceed n. Then what we should do? That means we can't use all the weights. Some weights have to be excluded. One weight could be in partial because we are doing in terms of maximum profit per unit of weight. So what we are saying is optimal solution will fill the knapsack fully. Why? Because you are allowed to take partially. So let's say if I taken first two weights properly, left with 2 kg or 2.5 kg, then I fill up to only 2.5 kg of next item. That means I can fill my knapsack completely. That means my sum Wi, Xi at the end is going to be equal to n. This is true for partial knapsack, but this will not be true for 0-1 knapsack. Knapsack meaning my Xi is either 1 or 0, Xi cannot be fractional, and that's the meaning of 0-1 knapsack. So look at, and when we look at the optimality, we'll prove this part. And primarily we're saying, if we are not optimal, look at the optimal solution and keep increasing weight to meet our that and say we end up becoming optimal, and I talk about that proof. But let's look at what is the algorithm basically look like. So we're given m as a knapsack weight, n is number of items, we are given profit of each item, we are given weight of item, and what we need to find is maximize Wi, Xi, and we assume that we have sorted them in the order that Pi Wi is greater than equal to Pi plus 1 by Wi plus 1 for each I. That means this is what I call is non-increasing. Non-increasing meaning Pi plus 1 Wi is going to be less than or equal to previous item. If it is decreasing, then this sign will only become greater than and not greater than equal to. So this is non-increasing, and if I had, so this is non-increasing and this would be decreasing. To understand the difference, should be clear about that part. So assuming these are sorted, if these are sorted in this order, all I need to do is start all the ways to 0, but I need to pick up. I take my variable u defined to capacity of m and look at each item at a time, assuming that in the order. So P1 by W1, so we are assuming that we sorted them out at P1 by W1 is greater than equal to P2 by W2 greater than equal to P3 by W3 and so on and so forth. That being the case, if my ith weight is more than u, that means I cannot pick this weight in full. That means, but this is the item that gives me maximum profit, I break. Otherwise, I take this item in full and go back to my loop. Decrease my weight by that much, go back to loop, and once I break, if my items are not full, then I take the partial weight, because remember I'm breaking at this point, so I need to take partial weight of Wi, and weight I'll take is Wi by u by Wi. Xi is u, remember Wi is greater than u, so I'll take a Xi partial u by Wi, because Wi is more, and that means till this I, let's say if I was 5, if I is 5, that means x1 is equal to 1, x2 is equal to 1, x3 is equal to 1, x4 is equal to 1, and my x5 would be whatever this is, let's say 0.5, 0.4, and whatever that is. And that is the basically what we call is partial or fractional knapsack problem. And now we prove that given this, the greedy knapsack generates an optimal solution. So how do we prove? We take the methodology. Let's say assume that ours is not an optimal solution. So that means there does exist an optimal solution. If it exists, that means the two solutions are different, because both are same, then we are optimal. So assuming we are not optimal, but there is an optimal solution that exists, and if there are two different solutions, that must differ. So look at the first xi. I could be 1, I could be 2, I could be 3, where my greedy approach solution differs from the optimal solution. And we saw that in the optimal solution that xi is equal to that of greedy solution without any loss of value, and this is how we prove. So let's look at the following. So this is a solution generated by my greedy approach with the weight wxi is equal to m, because for fractional knapsack my weight could be equal to m because my last item I take fraction, so I can always generate the weight. And let's say there's an optimal solution which is available, and we're saying if all xi equal to 1, solution is optimal because this is a trivial case. So we assume that my all xi's are not 1, so that means there is some j such that xj is not equal to 1, and in that case that means for all items less than j, my xi is 1. So let me repeat again. So let's say total I had n is equal to 10 items, and I picked up 6 items that, let's say m is 20. So I have put my x1 is 1, my x2 is 1, till x5 is 1, and my 6th item I take partially. So let's say x6 is 0.6, and then x7 is 0, x7 is 0, x8 is 0, x9 is 0, and x10 is 0 again. And that is what I'm basically depicting here. So for all i's which is less than j, for all I less than j, xi is 1. For jth item, this is more than or equal to 0 but less than 1, and for remaining all items greater than j, xi is 0. This is my solution obtained by my greedy approach. And consider there's an optimal solution which gives me yi to yn. Some may be more, some may be less. That doesn't really matter. And that means because this is an optimal solution, sigma w by y has to be m. With less than m, then I am feeling more knapsack. That can be the case. And now we need to find out how do we differ. Now consider some index k such that my yk is not equal to xk. That means till k minus 1, whatever my xk is same as yk. So find first k where my yk is not equal to xk, and then we see how we can become optimal from there. So graphically, if you look at, I'll probably show that the case. So assuming this is what I taken, my first j minus 1 element I picked in full, my jth element I pick in partial, and remaining n minus j element I'm not picking, which is 0. And let's say optimal solution is given by yi to yj, and my solution differs some k till this time k they are same, and some point in k which is not the same. And then we look at how do we approach and say that we are equally optimal and we are not worse than the optimal solution. So the following 3 cases are possible. So what we're saying is this is my solution. Till j minus 1 everything is 1. My jth case, sorry, I did the wrong diagram. Till j minus 1 everything is 1. My jth case is partial, and after jth item they are all 0. And the optimal solution is given by some yi, and we say find first index k such that this yk and my xk are different. So till k minus 1, x1 is y1, x2 is y2. So xk minus 1 is equal to yk minus 1, and they differ at some k. My xk is 1 and yk is not 1, because yk is 1, they will be same. This being the case, how do we compare? So we're saying case 1, k is less than j. If k is less than j, this diagram would exist, and we say y less than k, which is fine. Other possibility is k is equal to j. That means till j minus 1, we all happen to be same. My value is xj, this value is yk, and which is possible. And third possibility is k differ, k is more than j. Look at if k is more than j, what happens? Now, even you look at here in this case, when k is equal to j, yk is, this yk has to be less than xj. Because if it is not, so remember now this yk and this is xk again, because j is equal to k, so yk has to be less than xk. Because if it is not, if yk is greater than xk, if yk is greater than xk, then because y is a fraction weight, this will become more than 1, because we are saying wi xi is equal to m, and till this point in time we are all the same, and my xj happens to be less than yk, which gives me m, so this will be more than m, which is not feasible because maximum capacity, the solution cannot exist. That means yk has to be less than xk. And third possibility is k is greater than j. So till this point, if we look at, and we are saying this optimal solution, and we differ at some point here. Again, this cannot be possible because this weight already gives me m, and that means if I do some yk and this value is more than this, so this will give me more than greater than m, so this solution is not feasible. So we cannot have a case where k is greater than j. So only possibility is either k is less than j or k is equal to j. And we look at in both the two cases how our greedy approach solution is equal to our optimal solution. Consider in that way. So basically we'll take possible case greater than j, and yk is not equal to k, and yk has to be less than xk, because if it is not, then ours is a greedy approach. We are filling up with weight for profit. So by our logic of greedy approach, my xk has to be maximum, so my yk cannot be more than xk. And then what happens? In k is equal to xk, again same case, my yk has to be less than xk, otherwise this becomes more. So look at what really happens. Now consider and this third case is not possible. So how do we show that our solution is equally optimal? So we know that they differ from kth index. So what we do is increase yk. So let's say my xk happens to be 0.8 and yk happens to be 0.6. But for me, of course, xk plus 1 is equal to 0, where yk plus 1 may be 0.1, yk plus 2 could be, let's say, 0.2 or something, whatever that kind. Doesn't really matter. So what I do is, given this case, increase my yk to xk. That means an optimal solution, I'm increasing the amount of kth index, because if I'm increasing yi, this will exceed m. So for remaining items, yk plus 1 to yn, I need to reduce their values, because total sigma wi yi has to be m. This cannot increase. So if I'm increasing yk, this value has to be decreased accordingly, so that I maintain this, my lemma. So how do I proceed? Increase yk to xk and decrease that many such that, and that gives me new solution, such a way that x1 is equal to y1, x2 is equal to y2, xk is equal to yk, but other things differ. So my zi is equal to xi till I is equal to k, and zk is equal to xk, and then my yk plus 1, which is the value has decreased, so my zk plus 1 is less than yk plus 1, zk plus 2 could be less than equal to yk plus 2, and so on and so forth. So what happens is, because we are increasing so much, so whatever weight I am increasing of the kth element, remember I increase yk to xk, So whatever weight I increase, this is the weight I increase for all remaining items from k plus 1 onwards. I need to decrease the respective weight to make sure that my sigma wi yi remains equal to m. So I increase the yk to xk, I increase yk to xk and decrease the remaining weight such that the total weight remains the same. That means wk into zk minus yk is equivalent to this, and we'll take this property. Now given this, we have that my maximum profit pi zi, z is a new solution from optimal solution by changing yk to xk, which is sigma pi vi, previous weight, plus increased profit of kth element, because we increase the weight of yk to zk, which is actually xk, minus decreased profit of other items. This is what we did. Doing that, now you look at, we know that we ordered pk by wk is greater than equal to pk plus 1, wk plus 1 is greater than equal to pk plus 2 upon wk plus 2, and so on and so forth. That means this quantity which is greater than k, this quantity are less than this. Since these are negative, I can replace them by pkwk, and since the number become larger, they're negative, so this equal sign becomes greater than equal to what I'm doing. So this item comes as it is, this item comes as it is, and these are the ones which are getting replaced by pkwk. And since this pkwk is bigger than this, and this is negative, so this becomes my greater than equal to, from equal to greater than equal to, because I'm subtracting larger quantity. So if you look at from there, I know that this was equal to this, so this becomes 0. So my answer becomes sigma pi zi is greater than equal to, because greater than equal to pi yi. Now pi zi cannot be more than pi vi, because we said my yi's are optimal. That means sigma pi y is maximum, and we got a solution which says pi zi is more than equal to pi yi. That means this is a better solution, which cannot be the case. So that being the case, my pi zi cannot be more than y. That means it has to be equal to this, or when it is equal to this, the z is x and x is optimal. And if z is not equal to x, then that means we look at another element k which differs and repeat the process till we find either we say y is not optimal or x becomes optimal. So using this approach, we basically say my greedy approach gives me optimal solution whose profit could be same as another optimal solution, and that is what we're basically doing. To summarize, we look at the greedy approach for fractional knapsack. We approach is sort the weight in terms of profit per unit of weight, pick up the items in that order, and we pick up the items in that order. We keep picking item till we cannot pick item in full, and for the last item, pick in the fractional weight, and that will give us the optimal weight, and we prove that this solution would be as good as anything else. So I would recommend you to go through, look at the textbook, look at the slides, then any solutions available on the net, review it, and tomorrow's class we will discuss what is called job scheduling problem, and that again come from the second book. So tomorrow we'll discuss job scheduling problem, and then we go to greedy approach problem with basically graph problem. If any questions, please let me know. Otherwise, we'll close the discussion. Let me know if there are any discussions to be done. Any questions you ask, please ask me, or we will basically stop. If no question, thank you. And based on the PM speech today, we'll decide our course of action in next subsequent classes. Thank you.